Hello everyone, welcome to this lecture. Just to recap, in the last lecture we had introduced the RSA assumption. So, we will continue our discussion with RSA assumption. Specifically, the roadmap for this lecture is as follows. We will see a generic construction of public key crypto system from any given one way trapdoor permutation, and we will see how we can instantiate this framework by using the RSA trapdoor permutation to get the RSA public key crypto system, which we also call as the plain RSA public key crypto system. We will see several attacks on the plain RSA public key crypto system. Then we will see the COA or CPA secure variant of RSA public key crypto system, and finally we will end the lecture with some implementation issues which we face when we implement RSA in practice. So, let us begin our discussion with a generic framework regarding how we construct a public key crypto system from any one way trapdoor permutation. So, just to recall what sub one way trapdoor permutation scheme is, it is a collection of 3 algorithms. We have a parameter generation algorithm which outputs a public parameter and a secret parameter, which you can call as public key or secret public key and secret key. Then the function f is a 2 input function. It takes the public key pk and an input from the domain fancy x, and it gives you an output from the set fancy x, and it is always a deterministic algorithm. On the other hand, the inverse function, it is a 2 input function taking the secret key sk and the input from the codomain which you want to invert, and it gives you an output from the domain of the function f. And also this is a deterministic algorithm. We need 2 properties from any one way trapdoor permutation scheme. The first property is the correctness property, which requires that for every pair of keys output by the parameter generation algorithm and for every input little x, if you compute the value of f of x and then you compute the inverse of that function with respect to the secret key sk, then you should get back the output x. And the second property, which is the security property, is the one wayness requirement, which demands that your function f sub pk should be a one way function against a computationally bounded adversary, even if the adversary knows the description of the public key and the steps of your function little f. Now, given such one way trapdoor permutation scheme, our goal is to construct a public key crypto system which has a key generation algorithm, encryption algorithm and decryption algorithm over the plain text space, namely the set fancy x, and this is done as follows. So, the key generation algorithm of your encryption process will be basically to run the parameter generation algorithm of your trapdoor permutation scheme and obtain the public key and secret key pk comma sk, and we set pk as the encryption key and we set sk as the decryption key. To encrypt a plain text little m with respect to the public key pk, what we do is we just compute the value of the function f with the key pk on the input m. So, sorry for the typo here, this x should be m because we want to encrypt the plain text little m. So, this is the typo here. So, if we want to encrypt a plain text little m, then we evaluate the value of the function little f using pk as the public key on the input little m, and the resultant output, which I denote as little y, is considered as the ciphertext. On the other hand, if we want to decrypt a ciphertext using a secret key sk, then what we have to do is we have to call the inverse function of the trapdoor permutation scheme on the input c using the secret key sk to recover back the plain text little x. So, now let us instantiate this framework using the RSA one way trapdoor permutation. So, remember in the last lecture we have seen that RSA permutation can be considered as a one way trapdoor permutation scheme, and the details of the RSA trapdoor permutation scheme is as follows. So, the parameter generation algorithm for the RSA trapdoor permutation is as follows. It runs the gen modulus algorithm and outputs primes p and q of size little n bits and the modulus big N, where big N is the product of p and q. Then it computes the value of phi of n, namely the size of the set z n star, and phi of n will be the product of p minus 1 into q minus 1. Then it selects e which is greater than 1 such that e is co-prime to phi of n, and since e is co-prime to phi of n, we can compute the multiplicative inverse of e modulo phi of n, which we denote as d. And once we compute all these values, then the public key pk is set to be n comma e, whereas the secret key sk is set to be n comma d. The RSA function which takes an input little x from the set Zn star is computed as follows. To evaluate the value of this RSA function using the public key n comma e, we basically compute or output x to the power e modulo n, and x to the power e modulo n will also be an element of Zn star. On the other hand, if we want to invert the RSA function on some input y belonging to Zn star using the secret keys n comma d, then we basically output y to the power d modulo n. So, that is what is the RSA one way trapdoor permutation scheme. Assuming the one RSA problem is difficult to solve with respect to the gen RSA function, then we had proved or we had seen in the last lecture that we can use this RSA trapdoor permutation as a candidate one way trapdoor permutation. Now, let us instantiate the framework that we had seen in the last slide by using the RSA trapdoor permutation. So, we get what we call as RSA public key cryptosystem over the plain text space Zn star. So, the key generation algorithm for the RSA public key cryptosystem is we run the gen RSA algorithm of the RSA trapdoor permutation, and we set n comma e to be the encryption key and we set n comma d as the decryption key. So, the receiver will know n and d to decrypt the ciphertext, whereas the public key n comma e will be available in the public domain. If there is a sender which wants to encrypt a plain text little m using the public key n comma e, then it has to basically compute the RSA function on the input m, which is nothing but computing the value of m to the power e modulo n. On the other hand, if receiver receives a ciphertext little c, then using the secret key n comma d, it can to decrypt the ciphertext little c, it has to basically compute the inverse RSA function and output y to the power d modulo n. Right. So, the correctness of this RSA crypto system follows from the correctness of the generic framework that we had discussed in the last slide. Now, let us focus on the security of the RSA cipher that we have just constructed, and imagine that we have a receiver which runs the key generation algorithm of the RSA cipher that we have discussed, obtains the public parameter n comma e and the secret parameters n comma d, and it makes its public key n comma e available in the public domain, and say there is a sender which has a plain text m belonging to Zn star which it wants to communicate to the receiver. Then as per the syntax of RSA encryption scheme, it computes the ciphertext which is m to the power e modulo n, and the ciphertext is communicated to the receiver, and assume we have a polytime or computationally bounded eavesdropper who has eavesdropped the ciphertext. Now, one might be wondering that whether the following security argument is sound or not. We can say that if there is an adversary who has eavesdrops the ciphertext C and its goal is to recover the underlying plain text little m which is encrypted in C, then basically it has to solve an instance of RSA problem, because this adversary only knows the description of n comma e and it does not know the underlying m and it does not know the secret key little d. So, recovering m from little c is equivalent to solving an instance of RSA problem, and hence if we assume that the RSA assumption holds with respect to the gen RSA algorithm that the receiver has run, then we can argue that this scheme should be secure. But it turns out that this informal argument is completely flawed here. This intuition that recovering the underlying plain text from the ciphertext is equivalent to solving an instance of RSA problem is completely a flawed argument, and there are many reasons for doing that. There are many reasons behind this flaw. The first major flaw is that if you look closely into the RSA assumption, it holds only if the underlying m which is encrypted in C is uniformly randomly chosen from the set Zn star, which may not be the case in practice. In practice, sender might have any kind of plain text belonging to Zn star which she might be encrypting and producing the ciphertext C, whereas for RSA assumptions we need that underlying m should be a random element from the Zn star. The second flaw here is that even if we assume for the moment that sender is encrypting messages which are random elements from the set Zn star and hence the RSA assumption hold, the whole encryption process that the sender is using now is deterministic. There is no internal randomness which is there as part of the encryption algorithm. That means if the same sender wants to encrypt the same message little m multiple times using the same public key n comma e, then it will end up getting the same ciphertext little c. and throughout this course we have rigorously analyzed that how unsafe it is to use a non-random or deterministic encryption process. We can never hope that an encryption process can be CPA secure if we are using a deterministic encryption process. So, these are the two security flaws which are there with the so called RSA cipher that we have designed. It turns out that apart from this attack, that apart from this shortcoming that your RSA encryption process is deterministic, we can show several attacks on the plain RSA cipher. So, assume for the moment we are using the RSA cipher where the sender wants to encrypt random messages from ZN star, and we do not want the semantic security, namely we do not aim for indistinguishability based security. It suffice for us if adversary does not learn the entire plain text by eavesdropping upon the ciphertext. That is the notion of secrecy that we are aiming for right now. For the moment, assume that. It turns out that even if we go for this weaker notion of secrecy, namely all or nothing kind of secrecy, then there are several attacks which can be still launched on the plain RSA cipher. So, the first class of attacks is basically what we call as encrypting short messages using a small encryption exponent E. So, it turns out that for many practical instantiations of RSA, we set the public exponent or the encryption exponent little e to be 3 to ensure that the encryption process is fast, because if you see the encryption is basically compute the eth power of the plain text modulo n, and if I set e to be 3, then my encryption process will be very fast. It is fine that if I set e to be 3, then my d will be very large and my decryption process running time will be slow, but we can have some kind of trade off, and for most of the many practical instantiations this is a common trick which is used to make the encryption process fast. Now, assume we are using an instantiation of RSA where we have set e to be 3, and say we are considering we consider an application where the underlying messages are random elements from ZN star, but the magnitude of m is strictly less than the eth root of the modulus begin. And if you are wondering that what kind of applications encounter such kind of little m, if later on when we will see the hybrid RSA encryption, then the size of the modulus that we typically use is of size 1024 bits, and the message that we would like to encrypt to the hybrid RSA encryption will be roughly a 300 bit random string, a 300 bit uniformly random bit string, and we will set e to be 3. If that is the case, then the ciphertext will be m cube modulo n, but since my magnitude of m is strictly less than the cube root of n, m to the power e or m to the power 3 modulo n will be equivalent to the integer cube, and the effect of mod n will not take place at all. And if adversary is aware of the fact that we are using an application where the underlying plain text, its magnitude is strictly less than the cube root of the modulus n, then it also will be aware that the underlying little m which has been encrypted, its cube is actually contained in the ciphertext C, namely the integer cube, not the modular cube. And it is very easy to recover the underlying unknown m from the C by just finding a integer cube root of the ciphertext C, which can be computed in poly of the size of the modulus n amount of computation. So, that is a first class of attack, and we can have many other kinds of attack possible on plain RSA cipher. So, imagine for the moment that we are in a setting where the same we are considering an application where the same message needs to be encrypted and sent to multiple receivers. So, imagine we have say 3 receivers, receiver 1, 2, 3, each of it has its own modulus n1, n2 and n3 respectively, but each of them is using a same public exponent say 3, and of course different decryption exponent d1, d2, d3, where d1 is relatively where d1 is the multiplicative inverse of 3 modulo n1, d2 is the multiplicative inverse of 3 modulo n2 and so on. So, the public key which is available in the public domain are the respective public keys of the 3 receivers, and imagine that we have a sender which has a random message belonging to zn1 star as well as zn2 star as well as zn3 star randomly chosen, and say it wants to encrypt and send the same message to the 3 receivers. So, it will compute C1 which will be the m cube modulo n1, C2 which will be m cube modulo n2 and so on. Now, assume that this modulus n1, n2, n3 they are pairwise prime. If not, suppose for instance the GCD of Ni and Nj is not 1, they are not co-prime to each other, that means there exists a common factor of Ni and Nj, then using that common factor it is computationally easy to factorize either the modulus Ni or Nj, and say for instance if Ni is factorizable and since Ei is also publicly known, and if we know Ni's factors, right, we can compute the value of phi of Ni, and once we know phi of Ni and Ei we can compute the value of Di in polynomial amount of time, and if Di is computable then any encryption which is intended for the ith receiver can be decrypted by the adversary, right. So, it is safe to assume for the moment that pairwise all the modulus n1, n2, n3 they are co-prime to each other. Now, let me define a bigger modulus n star which is the product of all the 3 modulus here, namely n1, n2, n3, and since my underlying plain text little m which the sender has encrypted belongs to Zn1 star as well as Zn2 star as well as Zn3 star, that means m is strictly less than n1, it is strictly less than n2, it is strictly less than n3, that means the integer m cube will be strictly less than the bigger modulus n star. And now what I can do is, since my modulus n1, n2, n2, n3 and n1, n3 they are co-prime to each other, I can invoke a very nice result from the number theory which we call as the Chinese remainder theorem, which says that if your individual modulus n1, n2, n3 they are co-prime, then it is possible to compute the integer value m cube in polynomial amount of time, polynomial in the size of the respective modulus n1, n2, n3, such that recovered m cube basically satisfies the system of following modular equations. So, you are given the value C1 which is some integer m cube modulo n1 where m cube is not known, and you are given C2 which is some same unknown m cube modulo n2, and you are given the value of C3 which is the same unknown m cube modulo n3, and if your n1, n2, n3 the respective modulus they are co-prime to each other, then what basically Chinese remainder theorem says is it is possible to recover that unknown m cube in polynomial amount of computation. Then by applying the Chinese remainder theorem, an adversary who has eavesdropped this 3 cipher text C1, C2, C3 can apply the Chinese remainder theorem and recover the unknown m cube, and once the unknown integer m cube is recovered it can find out the exact m. So, again this is another attack which is possible on the plain RSA cipher, even if we assume that a sender's message which is a randomly chosen value from the underlying Zn star set. And it turns out that there could be several other possible attacks which can be launched on the plain RSA encryption process. So, this brings us to the concept of what we call as padded RSA public key crypto system, and basically the general idea here is that we have seen already that the plain RSA encryption process is a deterministic encryption process. There is no internal randomness hidden, and if there is no internal randomness then we can never hope to achieve CPA security. So, the idea behind the padded RSA encryption process is that we try to append some random bit strings to the plain text bits which we want to encrypt and make everything convert everything into a group element in the set Zn star, and then we apply the RSA function for encryption. On the other hand, at the decryption end we will chop off the random bit strings which we have added to the plain bit strings before encryption, and then that will be the recovered plain text. So, pictorially what we are trying to do here is the following. So, imagine that a receiver has done the public key setup, it has made its public key n comma e publicly available, where the size of the modulus big N is little n bits. Then the idea here is that the padded RSA encryption process, it will take another parameter little l, and the size of the plain text which this padded RSA encryption process will support will be of size n minus l minus 1 bits. That means you can encrypt any message in the set 0 comma 1 raised to power n minus l minus 1 bits, and the remaining l bits are reserved for a randomness. So, before encryption imagine you have a message m Along with that, you pad little l bits of randomness, which will be uniform randomness, and you will be left with one more bit, which we by default keep it as 0. If we do padding like that, and if we ensure that the resultant bit string, which will be of now length l bits, which we denote as m cap, we interpret it as an element of z n star. So, it might be possible that the resultant m concatenated with the randomness that we have appended may not lead you to an element of z n star, and if the resultant element is not an element of z n star, then it might look like that the encryption, the RSA encryption function and the RSA decryption function, they need not be mutually inverse function of each other. However, it turns out that even if the resultant m cap is not an element of z n star, but it belongs to z n, it suffice for us to apply the RSA function at the encryption end and to apply the RSA decryption function at the decryption end. We will, the correctness property will still hold if the padded m, when interpreted as an element of when interpreted as a group element, does not belong to z n star, but rather belong to z n. The correctness property that is there with respect to the RSA forward direction function and inverse function will still hold. We will prove that at the end of this lecture, but for the moment assume that the padded message m, which I denote by m cap, is an element of z n star, and then once we have m cap, to encrypt the message m cap or the group element m cap, we apply the RSA function, compute m cap raised to the power e modulo n. At the decryption end, the receiver who has the secret key n comma d, it will apply the RSA inverse function, namely it will compute c to the power d modulo n, and it will recover the group element m cap. And since it knows the value of little l here is a system parameter, it will be known both to the sender as well as to the receiver, and it will be publicly available. So, what the receiver can do is it can parse the recovered m cap as 0 followed by a plain text of length n minus l minus 1 bits followed by a randomness of little l bits, and it can simply ignore the randomness part, and the recovered thing or the remaining n minus l minus 1 bits is considered as the recovered plain text. So, as I said here, L is the publicly known public padding parameter, which is available both to the sender, receiver and to any third party. Now, it turns out that an adversary who is aware of the value of little l, it can launch a brute force attack over the amount of randomness or over the actual randomness which has been padded at the sender's end before encrypting the message. And complexity of the brute force attack is basically order 2 to the power O of 2 to the power l, because there could be 2 to the power little l number of candidate values of R, and to go over all those candidate randomness, adversary has to perform a computation of order 2 to the power little l. That automatically implies that if your little l is too short, that means the amount of randomness slot that is available in your version of padded RSA is too short. For instance, it is of order log of little n, then it is computationally easy to recover the underlying m, because a brute force of order 2 to the power log n is equivalent to a computation of order little n, which is polynomial in the security parameter. So, too short size of little l is dangerous. On the other hand, if you reserve a huge amount of slot for the randomness, but little slot for the actual plain text which you want to encrypt, then you can hope for a possible CPA security for the resultant instantiation of the padded CRSA, but the disadvantage will be that the actual message which we are going to encrypt, namely the actual bit string of length n minus l minus 1, will be very short. So, we have a kind of trade off here, and it turns out that there are several practical RSA standards which are available in the literature with different values of L, but unfortunately most of them do not have any kind of security proofs. However, we will use this blueprint and we will later return to the CCA secure versions of RSA Public-key Cryptosystem, where we will retain this blueprint, and there also the idea will be that we will take the actual plain text, which is a bit string, append it with some random pad, and then convert everything either as an element of Zn star or an element Zn, and encrypt it as per the RSA function, and at the decryption end we do the reverse operation. The kind of padding that we will use, that will ensure that we get a CCA secure version of RSA Public-key Cryptosystem. Finally, let me end this lecture with something related to the message space of Zn, and for that let me first state a property from the well known theorem from number theory, which I will not prove, which we also call as Fermat's little theorem. And what Fermat's little theorem basically says is that if p is a prime, then for every integer a which is not divisible by p, namely for every integer a such that a modulo p is not 0, then a to the power p minus 1 modulo p is 1. This holds for every integer a which is not divisible by the prime p. Now, what we are going to prove using this Fermat's little theorem is that, imagine if you have a modulus big N which is the product of two distinct primes p and q. That means your phi of n is nothing but the product of p minus 1 and q minus 1, and say you have two integers e comma d such that e and d are multiplicative inverse of each other modulo phi of n. That means e d modulo phi of n is 1. Then what we are going to show is that for every x in the set Zn, x to the power ed modulo n is going to give you x. Equivalently, this means that x to the power ed minus x is completely divisible by n. That is what we are going to prove. And it is easy to see that these two conditions are equivalent. Indeed, if indeed x to the power ed modulo n is x, that means when I divide x to the power ed by n, I get the remainder x. That means if I subtract that remainder x from x to the power ed, then that resultant number will be completely divisible by n. Now, before going into the proof of this theorem, what exactly is the significance of this theorem? The significance here is the RSA function and its corresponding inverse function will work even if I have an x which is not a member of Zn star, but rather a member of Zn. That means if we go and see the padded RSA where we are padding the bit string which we want to encrypt with a random pad and trying to interpret it as an element of Zn star, I said that it may not be an element of Zn star, because to be an element of Zn star the resultant element should be co-prime to your modulus big N, but that need not be the case. Your m cap need not be co-prime to n, but that is fine. This theorem says that even if you encrypt such m cap using the RSA function and try to decrypt it using the RSA function, you will get back the right m cap. Of course, remember that we have reserved the first bit in the padded RSA to be 0, which automatically ensures that m cap is definitely less than the modulus big N, and hence it is an element of Zn. So, let us proceed to prove this theorem. So, we take case 1. So, what basically we are going to do in this proof is we are going to prove certain properties with respect to x modulo p, and symmetrically we are going to prove similar properties with respect to x modulo q, and then we will combine these two properties to arrive at the proof of this theorem. So, let us first consider case 1 where we are going to see the properties of x modulo p, and we can have two sub cases here. If x modulo p is 0, that means if x is completely divisible by p, then so is x to the power ed, right. And if x to the power ed is divisible by p, and if x is also divisible by p, then it implies automatically that x to the power ed minus x is also divisible by p. So, that is sub case 1, and sub case 2 here is when x modulo p is not 0, that means x is not completely divisible by 0, and in this case I can invoke my Fermat's little theorem, and I can say that x to the power p minus 1 modulo p is 1. And now, what I am going to do is I am going to use the fact that ed modulo phi of n is 1, right. Remember, my ed modulo phi of n is 1, and also my phi of n is the product of p minus 1 and q minus 1. That means, I can rewrite my e times d as some multiple of p minus 1 times q minus 1, namely say k times some k times p minus 1 q minus 1 plus 1. Plus 1, because ed gives the remainder 1 on divided by phi of n. And now, what I can do is, if I want to find out the value of x to the power ed modulo p, I know that ed is nothing but k times p minus 1 q minus 1 plus 1. So, I can rewrite x to the power ed modulo p as x to the power p minus 1 whole raised to power k times q minus 1, and this plus 1 will contribute another x modulo p. So, that is what x to the power e modulo p will be, and I know that x to the power p minus 1 modulo p is 1. That means this thing is nothing but 1, and 1 raised to power k times q minus 1 is going to give me 1 only. That means, this entire first bracket is going to give me 1. So, that means I can say that x to the power e d modulo p is nothing but x modulo p, right. So, that means with respect to x modulo p in subcase 1, if x is already divisible by p, then I can say that x to the power e d minus x is completely divisible by p, and in the second subcase also I am establishing that even if x modulo p is not 0, I have established that x to the power e d modulo p is same as x modulo p. That means, both x to the power e d as well as x gives the same remainder on divided by p, and as a result I can say that their difference, namely x to the power e d minus x, is completely divisible by p, right. So, it does not matter whether x is divisible by p or not. I have established here that x to the power e d minus x is completely divisible by p, and symmetrically I can do the same argument for x modulo q as well. So, with respect to x and q, I have two subcases. If x is already divisible by q, then so is x to the power e d, and hence I can easily conclude that x to the power e d minus x is completely divisible by q. On the other hand, for the case when x is not divisible by q, I can apply Fermat's little theorem here, and I can say that x to the power q minus 1 modulo q is 1, and then using the similar argument that I have used for the case of x and modulo x and p, namely I can use the fact that E d is k times p minus 1 q minus 1 plus 1, and then I can rewrite x to the power E d as x to the power q minus 1 whole raised to power k times p minus 1 multiplied by x modulo q. And I know that since x to the power q minus 1, I know that overall it turns out to only x modulo q. That means, x to the power e d as well as x gives me the same remainder on divided by q, and hence I can say that x to the power e d minus x is completely divisible by q, right. So, these are the properties that I have established now. That means, I have shown that x to the power e d minus x is individually divisible by primes p as by prime p as well as prime q, and since my primes p and q are distinct, it automatically implies that x to the power e d minus x is also going to be divisible by n, because n is my product of p and q, and that establishes this theorem. Now, let us see how we can apply the Chinese remainder theorem for fast RSA encryption and decryption, because this is a common trick which we use during the real world instantiation of RSA function. So, if you see the RSA encryption function and decryption function, then both of them requires modular exponentiation. To encrypt, we need to perform a compute x to the power e modulo n, and to decrypt we need to perform ciphertext raised to power d modulo n. Now, even though we have not yet discussed the best known algorithms for computing modular exponentiation, if time permits we will discuss one of such algorithms in our subsequent lecture. It turns out that the best known algorithm for performing modular exponentiation modulo little l bit integer requires amount of time, which is c times some l cube, where c is some constant. That means, if my modulus big N is of size little n bits, then to perform both RSA encryption as well as decryption function, I need to perform c times n cube operation. Now, what Chinese remainder theorem says is, if since n is a product of two primes p and q, where the two factors p and q are co-prime to each other, then basically Chinese remainder theorem gives you a bijection, namely a 1 to 1 onto mapping from the set Zn star to the Cartesian product of the set Zp star and Zq star. Remember, Zn star is basically the set of all integers in the range 1 to n minus 1 which are co-prime to big N. In the same way, Zp star is basically the set 1 to p minus 1, basically the set of integers in the range 1 to p minus 1 which are co-prime to p, but since p is prime, the set Zp star is nothing but the entire set 1 to p minus 1, and in the same way the set Zq star is the entire set 1 to q minus 1. So, what the Chinese remainder theorem does is it defines a very nice bijection from the set Zn star to the Cartesian product of Zn p star and Zq star, where any element little a belonging to the set Z n star, it is mapped to the following pair of elements. You take the remainder of a modulo p and the remainder of a modulo q. That will be the representation of the element a belonging to Z n star in the set Z p star and the set Z q star respectively. And not only that, what Chinese remainder theorem basically shows is, tells you that if you are performing some computation in the set Z n star, say if you are evaluating the value of f of a modulo n, then the same computation you can carry over individually in Z p star and Z q star, and you will get a representation of the result of f a modulo n. That means, instead of performing f a modulo n, you can perform f a modulo p and f a modulo q, and that resultant pair of elements can be considered as the representation of your result f a modulo n. So, that is how you can interpret this Chinese remainder theorem bijection. That means, if I consider the decryption function, for the moment I am assuming that my public exponent e is 3, that takes care of the encryption part of the RSA function. RSA encryption process will be very fast if I set my e to be 3. But my problem will be the decryption. I want to speed up my decryption process. So, since my decryption function requires me to compute y to the power d modulo n, by applying the Chinese remainder theorem, the element y to the power d modulo n, which is an element of Z n star, can be interpreted as a pair of elements from one from Z p star and another from Z q star, where the representation from Z p star will be y to the power d modulo p and the representation from Z q star will be y to the power d modulo q. Now, since y is relatively prime to p as well as relatively prime to q, and if indeed that is the case, it turns out that we can prove that y to the power d modulo p is same as y to the power d modulo p minus 1 modulo p. That means, in the exponent I can reduce my exponent d to d modulo p minus 1, and I call this value to be y sub p, and the same holds for y to the power d modulo q as well. That is, in the exponent I can reduce the exponent d from d to d modulo q minus 1, and let me call this value to be y q. That means, this y to the power d modulo n can be written as or expressed as the pair of elements y sub p comma y sub q as per the Chinese remainder theorem. That means, if you know how to compute y sub p and y sub q, then using the Chinese remainder theorem you can obtain the result y to the power d modulo n. That is what Chinese remainder theorem ensures for you. Now, let us try to analyze how fast it is to compute y sub p and y sub q. Before going into that, let me tell you that since d is known to the receiver who is going to run the decryption algorithm, and p minus 1 is also known to the receiver, right, because it knows the factors p and q. So, d modulo p minus 1 can be pre-computed by the receiver and can be stored once for all, and same holds for d modulo q minus 1 as well, right. So, d and q are also known to the receiver or the person who is going to run the decryption algorithm, and hence d to d modulo q minus 1 can be pre-computed in advance by the receiver. Now, it turns out that using the Chinese remainder theorem, computing y to the power d modulo n requires you to perform 2 times c n cube over 8 or n cube over 4 times computation. This is because my n is the product of 2 primes p and q, and my size of n is roughly of n bits, little n bits. Since n is the product of p and q, that means the size of the prime factors p and q that we are using here is roughly of size n by 2 bits each. That means, to compute y to the power d modulo p minus 1 modulo p or the value y p, I need to perform a modular exponentiation where the size of the modulus is n over 2 bits. And by using the best known algorithm, that will require me to perform computations of order c times n cube by 8. And similarly, to compute y sub q, I need to perform computation of order c n cube over 8, and if I sum these two things, I get that the total computation that I need to perform to compute y sub p and y sub q will be 2 times c n cube over 8, which is basically c times n cube over 8, and this is simply 25% saving compared to the naive way of performing or calculating y to the power d modulo n directly. If instead of computing y to the power d modulo n directly, we use this indirect approach where we compute y sub p, y sub q in zp star zq star and then combine it to obtain the result y to the power d modulo n, we basically end up saving 25% of computation. And this is a very common trick which is used in the practical instantiations of the RSA decryption algorithm. Now, let me end this lecture by showing you some more attacks on RSA. Namely, I want to show you that how dangerous it could be to share public parameters across multiple users in the context of RSA crypto system. So, I am going to show you one of the simplest possible attack which we call as common modulus attack. There are other sophisticated attacks which are also possible, but I am not going to discuss them. And this is kind of very different compared to Elgamal encryption scheme, where we have seen that in the context of Elgamal encryption scheme, sharing public parameters, namely sharing the description of the group, the description of the generator across multiple receivers is fine. That means, it is fine if multiple receivers use the same cyclic group to instantiate their Elgamal encryption scheme, the same generator to instantiate their Elgamal encryption scheme and so on. But when it comes to RSA, it might be extremely unsafe to share public parameters across multiple users. So, the attack here is as follows: assume a company which is using the same modulus begin for each of its employee. That means, every time a new employee joins the company, you can imagine that the company retains the same modulus begin for the employee, but what it does it generates a fresh independent public exponent EI for that user and corresponding decryption key DI for the same user, such that EI and DI are co-prime modulo n. So, for the moment, assume we have 3 employees in the organization. The first employee has its secret decryption key D1, the second employee has its secret decryption key D2, and in the same way the third employee has its secret decryption key D3. And we know that property wise EI and DI, they are multiplicative inverse of each other modulo phi of n. Now, it turns out that again by using a well known fact from number theory, we can prove that if we are given the modulus begin and EI comma DI such that EI and DI are multiplicative inverse of each other. So, I beg your pardon here, it should not be E1 times D1 here, it should be EI times DI, that is a typo here. So, if we know the modulus begin, if we know the value of EI and we know the value of DI such that EI and DI are multiplicative inverse of each other modulo phi of n, where phi of n is not known to us, then we can compute the value of phi of n in poly of size of modulus n time. That means, if for instance employee 1 is considered here, since it knows its public exponent E1 as well as its decryption exponent D1, but it does not know the value of unknown phi of n, by using this fact from the number theory and using that algorithm, it can compute in polynomial amount of time the value of phi of n. And once phi of n is computed by the employee 1, since it knows the value of E2, right, namely the public exponent public key of the second employee, and it knows the modulus begin, then by using the same result from number theory, it can compute D2, and in the same way it can compute the result of it can compute the value of the decryption exponent of the third employee as well. And once it knows the value of D2 and D3, then any private communication which is happening between the second and the third employee using RSA encryption scheme, even if it is a padded RSA encryption scheme which is randomized for the moment, assume that since the value of D2 and D3 is known completely to the employee 1, it can completely find out what exactly is happening between employee 2 and 3. Right. So, that shows that how unsafe it might be if we end up having multiple users having the same public exponent same modulus begin. It is highly dangerous. So, that brings me to the end of this lecture. Just to summarize, in this lecture we have seen that how we can instantiate a public key encryption scheme from any one-way trapdoor permutation, and we have shown that how we can instantiate this framework using the RSA trapdoor permutation and get what we call as plain RSA cipher. But plain RSA cipher cannot be used in practice because first of all it is not randomized, and secondly we cannot directly reduce its security to the RSA problem. We have seen how we can make RSA encryption randomized encryption process by doing padding, and we have seen that how we can speed up the RSA decryption function using Chinese remainder theorem. Yeah, thank you.